Good morning. I'm Stan Sclaroff, and there are a number of different research projects in our group. Some will be presented as posters later today. I wanted to talk about a project which won't be included in a poster, which is about learning to embed while learning to rank. It's collaborative work with a number of students who I'll mention at the end of the talk. And it's also sponsored by, or been funded by a couple of industrial partners, and I'll also show that at the end of the talk as well. So nearest neighbor retrieval has many applications in computer vision. There are a few examples shown in this slide. For instance, if I'm shopping and I want to find a purse of a particular color or shape, image retrieval can find nearest neighbors and present similar objects while I'm shopping. Or if I'm navigating in the world or trying to localize where I am based on images, I can match an incoming image from my camera, let's say on my vehicle, to some data set that I've captured before to localize where I am as I'm driving around a city or as I'm viewing a landmark in Boston to get information. In this case, the retrieval problem is given image patches in the images that I have in my data set. I want to quickly identify the matching image patches in the incoming image stream from my camera so that I can align the images and begin to analyze where I am and register those images. So in that case, there are two databases. One is the database of images that I've collected before, and the other is actually a virtual database of the incoming image stream where I want to do matching. Another example of nearest neighbor retrieval in computer vision might be identifying object classes based on sub-images. So I might use some sort of saliency measure to extract the salient patches within the scene, and then use those patches as input to a retrieval system where I have a collection of images that have labels, and then by virtue of retrieving similar looking images, I can then inherit the labels from the images that were labeled before. These are just a few examples of nearest neighbor retrieval in computer vision. There are many of them. It's really a workhorse of machine learning in general, as I think Daria had explained in her talk as well. It's applicable at the nexus of vision and language, but also in language. So what we'd like to do is capture semantic similarities between objects. And to do that, what we're going to do is take a high-dimensional input, an image, and map it through a model, which is a deep model. Shown here, it's a convolutional network, to produce a low-level embedding or encoding that gives me an address or a vector, an embedding space that preserves the similarity of the objects. Okay? So the database index in this case is a collection of vectors that represent the high-dimensional objects. And with each of those vectors, we can actually store any labels that we've acquired. Objects don't all need to be labeled. They can be mapped into this space without labels. And then the neighborhood structure can help us to label the unlabeled objects that we encounter. A very famous way to do this is to use hashing methods where the embedding is a binary embedding, and then the similarity is measured in a Hamming space. So we've got a vector of 0 and 1s, and our goal is to learn a model which will effectively map similar inputs to binary vectors that when I measure the Hamming distance between them, similar objects map to similar codes and therefore have small Hamming distances. This is really space efficient. So it's a very popular approach. You may be familiar with some methods which are called data-independent approaches, like locality-sensitive hashing. It's a workhorse of image retrieval methods, but also Shazam, the app that allows you to retrieve similar music based on clips that you record with your handheld device. But it's a data-independent method in that it's not trained for specific types of objects. And it actually turns out that data-dependent methods can easily outperform methods like locality-sensitive hashing. Nevertheless, the advantage of data-independent approaches is that they're efficient. They need no training data. But if there's training data available, data-dependent methods will work better, and our methods that I'll describe today fall into the latter category. One challenge that arises when considering learning models for doing hashing or nearest neighbor retrieval is that a lot of approaches assume that we have a batch, meaning that we're given all of the training data at once and we train the model once. And what this does is that it has a number of disadvantages, but chief among them is that as new classes arrive and I need to incorporate them into my representation, I need to retrain from scratch. That's really not workable in the real world, where you're adding new things to corpora or image data sets, new types of classes appear, or you fire up a new app on a handheld device and you start taking images and you start from zero. And you keep adding new things and labels, etc. You want the system to evolve its representation over time. Retraining from scratch is just too expensive. It's got quadratic complexity at least. So what we propose to do instead is to take an online approach where as the data comes in, we can actually update our method by using stochastic gradient descent. Without going into much detail, I do want to brag a bit about the students who I've collaborated with over the years, who can go back into the literature and find things that are more than 5 years ago that are relevant to the research projects that we're working on. I think that this is a key skill because in mathematics, there are lots of really great results that are from centuries ago that are relevant today suddenly, right? And in the field of AI and computer vision, we find also that there are results that if we reach back far enough, they're really key in solving problems that we have today. One such algorithm is called reservoir sampling. So a reservoir sampling method is really easy to explain. Let's say I've got a stream coming in and I want to draw what is an approximate independent sampling uniformly at random from the incoming stream, and I want to have a representative subset. So I'm just going to at any time have a buffer which has a sample set in it that's representative of everything I've seen so far. And every time a new item comes in, I flip a coin and I decide whether to vacate an item in the reservoir or not. That's the basic idea. And using a reservoir of this type, I can evaluate the model's performance and see what mistakes it makes. And as it makes mistakes, if it makes mistakes greater than a certain threshold, then I need to go back and adjust my model. So I can defer updates to my model as the stream is coming in. And if things are not changing very much, then I don't need to work at all in maintaining the model because it's relatively up to date, subject to some measure of an error rate. Another contribution that we've developed in our lab is to look at different loss functions for learning these hash functions. One thread of work that we've followed is to look at the mutual information. You can think of it as just evaluating the degree of separation between the blue class and the red class. So the horizontal axis in this graph is just the number of bits that are different between the encodings of the different vectors for different objects. So what we want is the number of differences between the vectors for the blue items to be small, because the query is a blue item. And the red items should be large. Ideally, those two should be completely separated. And mutual information gives us one measure for this. But since it's based on a histogram, it presents some problems when we look at evaluating the loss. In backpropagation, we need derivatives. So if we look at taking the partial derivatives, there are terms here that are easy to compute. They can be evaluated in closed form. And there are also other terms which cannot be evaluated in closed form. And so here we have a more recent paper that we can rely on for our solution. The basic idea is very simple. In order to be able to take derivatives of a histogram, we can use interpolants over the bins. and then use those interpolants as proxies for taking the derivatives in our backpropagation paths. It's very simple. All right. And then there's some other things that we need to do to relax our formulation and make it differentiable, and then learning can proceed. The end result is that if you look at our performance on some standard benchmarks for the online case, our method performs much better than the state of the art. Another way to look at this is in terms of ranking. So in retrieval, really what matters is that the most relevant items are ranked first. So when I do a query on the web, or I do an image retrieval from, let's say, Google image search, I want the most relevant images to appear first, so that I don't have to look down the list to find the relevant items. So mutual information correlates well with this. So what you see here is a query, and pluses mean that the item was relevant. And so if all of the pluses appeared in the first part of the list, then this would be really good performance. And a measure of that is called average precision. So in this case, the average precision is quite good because all the pluses are at the first position and all the minuses are later. But this begs the question, why are we using mutual information as a proxy for average precision? Why don't we optimize it directly? Well, this presents some really interesting problems actually when we look at ranking, because if we're looking at bits, the differences in the number of bits, it could be that some items with a number of bits that are different are relevant and some are not. So they have an equal number of bits that are different, but we have what are called ties, meaning that they have the same distance, some are relevant and some are not. So in this case, the AP, if I cheated, I could, well, actually, there are papers out there that I don't think that are cheating, but let's say that I were a cheater. So I could, with the output here, the circle is tied with the triangle in this first position for distance 0, meaning no bits are different. This is the pessimistic version. The triangle's in the first position, and the AP is much worse. Or I could actually compute the expected value of AP over all possible combinations, but it would be just too complex to compute it. Again, there's a lovely paper from more than 5 years ago that's relevant to our problem. In the information retrieval literature, they actually have provided us with closed-form formulas for the expected value for the mean AP, and also for another measure, which is called the DCG. All right, so given these, what we have are what we call tie-aware metrics, meaning that we're aware that there could be ties, and we account for them. And using this approach, we can actually gain state-of-the-art performance in retrieval benchmarks by exploiting this tie awareness. More importantly, we make the observation that when the number of bits is relatively small, then tie awareness is crucial. And that makes sense, right? Because we're using a smaller range of quantization values, so we get many more ties. And this also is important when we want to come up with a very small footprint in our encoding. So this then begs the question, how can we apply this to the image matching problem? And again, tie awareness and average precision can be taken into account. This is a learning to rank problem where what we're doing is we're ranking patches that could match. Given an input patch and given an image that we want to match against, we go over the salient patches in it and then we rank them and see which ones are most similar and consider those as matches first. Okay? Now, the standard approach to doing this kind of learning in the literature is to look at pairs. But you can quickly determine that taking all possible combinations of pairs is difficult. Most of the pairs are easy, but some are very difficult to actually correctly order. This is called hard negatives mining. Instead, in our approach, what actually we can do is we can learn over the full ranking of the full list directly in closed form. The end result is that we get the state-of-the-art performance on a very important current patch matching benchmark over 3 different tasks: patch verification, patch retrieval, and image matching. Now bear with me while I explain this graph because it's a bit dense. So the benchmark itself is broken up into easy patches that are easy to match, hard patches that are difficult to match for methods, and tough, which is sort of in between, or I guess difficult, even more difficult. So these graphs at the bottom here, the bars show the average performance over everything. The red shows the performance over the tough cases, the purple over the hard cases, and the easy cases. Our methods shown at the bottom here do quite well over all classes against the leading technique in the literature, as you can see there. Now, there are other benchmarks that I'm not describing in this talk. What's really interesting is that SIFT is not a learned description for patch matching for these kinds of image matching problems. SIFT descriptors have been the dominant descriptor. They're very difficult to beat, frustrating actually, because you'd think that machine learning would be able to beat a descriptor that's just defined a priori without learning for some data set. And our method is the first method to beat SIFT, fair and square. So to summarize, I described our research in learning deep embeddings while learning to rank. I talked a bit about learning to hash and also about local feature descriptors. I want to credit the collaborators in this project, including Yan Lu, who was an industrial collaborator, and also our industrial support at Adobe, Hikvision, and Honda. Thank you.